Section 7.3, Polar Coordinates. So at this point we've discussed parametric equations in a couple of different manners. Now we want to turn our attention to an arbitrary point in the xy plane. So if we take this point that I have here, P, the point xy, can we represent this point based on the radius, the r there, and the theta, the angle? Well, using some trigonometry, we can say the cosine of theta equals the adjacent over the hypotenuse, that is x over r, so that x equals r cosine theta. All right. Similarly, we can show that y equals r sine theta, and using our trigonometric identity that we have can show that r squared equals x squared plus y squared. That's actually the Pythagorean identity. And the tangent of theta is going to be y divided by x by taking the ratio of those two things. So we want to take that information along with the restriction that our theta, our angle, is between 0 and 2 pi, and we are going to convert each of these points that we have, that we're given, xy, into a unique polar coordinate, r theta. So we're going to use these bits of information very much. So first, the point 1, 1. This is in our xy plane. We can begin by saying r squared equals 1 squared plus 1 squared, which is 2, so that r is the square root of 2. All right, simple enough. So this point is going to be converted into square root of 2, and then we want our angle theta. Now the easiest of these three to use is going to be tangent, if it applies. We'll see a case where it doesn't. Tangent of theta is going to be y divided by x, which is 1, and then that implies that theta is pi over 4. Square root of 2 over square root of 2, 1. So theta is pi over 4. So our point is square root of 2 pi over 4. This is actually an alternate way to view the xy plane. That's why it's actually called polar coordinates. Instead of Cartesian, like we deal with usually, we're looking at polar coordinates. We'll see this in just a minute. A lot clearer, hopefully. Next, we take the point negative 3, 4. All right, well, r squared equals negative 3 squared plus 4 squared, which is 9 and 16, 25, which means that r equals 5. So in our point, 5, comma, and now we'll take tangent theta equals y divided by x. That would be negative 4/3, which would mean that theta is actually negative 0.927. Now that does not agree with our theta being between 0 and 2 pi, so if we alter that by pi, if we add pi to that, our theta is roughly 2.21. So our point then is 5, 2.1. Alright, C, we'll take 0, 3. R squared equals 0 squared plus 3 squared, which is going to be 9, which makes r 3. And then we'll take our tangent theta equals 3 divided by 0. And this is where we cannot actually use our tangent. So let's take what we know about r. I'm going to go ahead and take the equation sine theta. Sine theta equals y over r. So our y coordinate is 3. Our r we found is 3, which makes theta equal to pi over 2. So our point is 3 pi over 2. Last one of these, r squared equals 5 square roots of 3 squared plus 5 squared. That is going to add up to be 100, which makes r equal to 10. So our point is going to be 10, something. Now our tangent theta is going to be equal to negative 5 over 5 root 3. right, which is negative 1 over root 3. And so theta is negative pi over 6. Now that is not between, it's not between 0 and 2 pi like we want. So we will add pi to that. So that would be 5 pi over 6. So our point is 10, 5 pi over 6. Example 2, convert, actually no, it's still example 1, it's a long one. Convert each of these into rectangular coordinates. All right, this is going to be a whole lot quicker because we have these equations. We know what r and theta are, and we want x and y. We can plug those into r cosine theta and r sine theta. So for the first, our x is going to be 3 cosine pi over 3, which is 3 halves. So we have the point, just put it over here, 3 over 2. And then y is going to be r times sine of pi over 3. So that will be 3 root 3 over 2. So 3 root 3 over 2. And there's our rectangular coordinate from our polar. Same idea here. X is r times cosine 3 pi over 2. And y will be 2 sine of 3 pi over 2. You were likely told at some point that sine is a y value. That's the way I like to think of it. And our cosine is our x value. That actually corresponds to this way of thinking. So, all right, so that means x is 0 because our cosine is 0 there. And our y at 3 pi over 2, that is negative 1. So our point is 0, negative 2. G, x equals 6 cosine of negative 5 pi over 6, and y is 6 times sine of negative 5 pi over 6. So for the first, okay, x is going to be negative 3 root 3. Negative 3 root 3. And our y value is going to be negative 3. Which means our point is negative 3 root 3, comma, negative 3. Alright, moving on. Here is the polar coordinate grid. Okay, if you notice there is the polar axis. That is actually how we determine our radius. If you notice, this is made up of concentric circles. Whereas where this line right here, this circle, is r equals 1, r equals 2, 3, 4, and 5. And our radian angle measures from 0, pi over 2, pi, 3 pi over 2, all the way around to 2 pi. Now we said we restricted our angles to be between 0 and 2 pi so that these are somewhat uniquely defined. All right, so what we're going to do is plot some points in this plane. The first is 2 comma pi over 4. That means a radius of 2. So I'm actually living on this circle here. And I want to go to an angle of pi over 4, which would be this point right here. All right, so my point for part A is that right there. All right, for part B, I'm living on the circle with a radius of 3. See if I can just label that clearly right there. There's a radius of 3, and I'm going to 2 pi over 3. So if we're on this circle and we go to 2 pi over 3, this is not where my point's going to be because my radius here is negative 3. So rather than actually going here, I'm going to go in the opposite direction. So it's actually going to be over here at 5 pi over 3 with a radius of 3. Right, so a negative radius travels backwards. We're traversing in the opposite direction. Last point here, 5 pi over 4. So a radius of 4, I am living on this circle, and I'm going to 5 pi over 4, which happens to be right over here. So I'm on this circle, and I'm going over to 5 pi over 4, so this point right here. That is my point for part C. All right, example 3, graph the curve defined by the function r equals 4 sine theta. Identify the curve, and then rewrite the equation in rectangular coordinates. All right, so to graph this, I'm just going to use this table of points. This is just taking various values of theta and evaluating. Okay, same way you would with x and y for our independent dependent. Here, our independent is theta, and our dependent is r, so we just do the exact same thing. So if we evaluate it at 0, we get 0. At pi, we get 0, etc. We get lots of points here. So I'm going to go ahead and plot these points in blue. So 0, 0. A theta of pi over 6, my radius is 2. Alright. There's a point right there. At pi over 4, I'm at 2.8. So we're looking more something like that. 3.4 at pi thirds for my radius. Pi halves, I'm at 4. Okay. 2 pi over 3, 3.4. Something like that. 3 pi over 4, it is 2.8. That doesn't seem right. 2.8. A little less. And 2 at 5 pi over 6. Okay, and let's see. Okay, pi is 0. So we're right back there again. 7 pi over 6 is negative 2. If you notice, that's actually going to end me up right here. So these negative values for our radius are all going to end up, instead of here and here, they're going to end up here and here respectively. So it appears that this actually might be forming what looks like a circle, or at least some strange version of a circle. Right, so I want to go ahead and claim that that's a circle. Now, rewrite the function in rectangular coordinates. So I'm going to use some space over here. So I've got the function r equals 4 sine theta. Now there are a few identities I want to hold on to. Y equals r sine theta. X equals r cosine theta. And r squared equals x squared plus y squared. So to begin with, I'd really like to make this equation in the form of r squared. That would be great. So I'm going to multiply the whole equation by r, so that I get r squared equals 4r sine theta. Now if you notice, I now have r sine theta, which I can say is y. So this is r squared equals 4y. Well, r squared is x squared plus y squared equals 4y. There's my equation. Now, some more algebra. I can subtract the 4y to both sides. Back. Equals 0. And what I'm going to do is complete the square. I'm going to complete the square here. And that would be a perfect square if I had a value of 4 there. And so this is x squared plus y minus 2 squared equals 4, which is a circle. Okay. With radius, with a radius of 2, centered at the point 0, 2. Which, if you go back to that graph, I think you might be able to agree that the center of that circle is 0, 2. And there we have it. And we will actually use this technique several times in another section to write equations this way. Now let's rewrite some other equations in rectangular coordinates and then identify the graph. Alright, so we're going to still use those same identities. X equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared. Alright, so theta equals pi thirds. That graph is regardless of the radius value. The angle is pi over 3. So we actually get something that is a line. This line is going to be y equals tangent of pi over 3x. The slope is going to be the tangent of that angle. So that is y equals square root of 3x. Part B, r equals 3. That is going to be a fixed radius of 3 cycled around. Now I'm going to go ahead and write this as r squared equals, well, r squared is 9, which means x squared plus y squared equals 9. This is a circle of radius 3. And this was a line of slope equal to square root of 3, which is the tangent of pi over 3. Oh, we should add in here, that is centered at 0, 0. Alright, r equals 6 cosine theta minus 8 sine theta. Alright, let's go ahead and replace some things. Actually, first we want to square both sides, or multiply by r on both sides, so we get an r squared. And so 6r cosine theta minus 8r sine theta. That would be x squared plus y squared. And this would be 6x minus 8y moving everything to one side, minus 6x. I'm going to leave some space because we are going to want to complete the square for both of these. Y squared minus 8y plus something equals 0. Plus, and we're going to add two things. Well, on the left side, for the x's here, that would be plus 9. So go ahead and add 9 there. And the second one would be 16. Do that in a different color. 16, 16. So we have equals 25. And then this will factor as y minus 4 squared and x minus 3 squared. So this is a circle. Okay, centered at the point 3, 4 with a radius of 5. Now I have a chart here that I actually copied straight from the book, so if it's a little unclear, you can always reference it there. At the bottom of the page is a link to that textbook. But this is actually from the textbook of some very common functions. So common polar functions. The first is a line passing through the pole, that is 0, 0. with a slope of tangent k. That was our first example. The second is a circle where we have A and B there. We'll talk about this more in 7.5. A circle centered somewhere. We then have a spiral, which is very interesting because it shows up in nature quite often. You probably have heard of the nautilus shell at some point. If you hadn't, you should just look up nautilus shell, and it looks a lot like that equation right there. All right, here are a couple more. The next is a cardioid. Okay, and there's the equation. They would look something like that. I do not know how to say this one, so I'm not even going to try. And then we have the rows, okay, which is 3 sine 2 theta. So it's of the form A cosine with some factor B times theta of a sine or cosine. And if you see a graph that looks like one of those, then the function or the equation is going to be of those forms. And vice versa. If you see a function with that certain form, then the graph's going to look like that. Now, there are lots of ways to graph these, to actually envision them. I would suggest you check out desmos.com or some other polar graphing site. All right. We have 2 examples left. The figure below shows a curve that is often used to model the nautilus shell. How can we describe this curve mathematically? Well, based on what we saw earlier in that table, this is of the form A equals B cosine theta. And being centered at 0, that actually tells us something about the equation. This is actually going to be, because this varies based on theta, now there's a constant that it sort of varies with, but what's happening here is the distance from our point P, and I'm going to go ahead and label it P of xy, to the origin, let's go ahead and label that 0, is varying by theta. You can kind of see that theta is just ranging from 0 to 2 pi, and the distance that point is going is varying by some constant. Okay, so that would be, if we found the distance between that point to 0 in xy coordinate system in the Cartesian plane, that would be the square root of x squared plus y squared. And that would be equal to k theta. Now we know from an earlier equation that tangent theta equals y over x. Okay, so if tangent theta equals y over x, then theta is going to be tangent inverse of y over x. Now we can't figure out exactly what that constant k is, so we're not going to worry too much about that. But if we try to isolate y here, you might notice we really can't do that very well. We could do something like this, though. We can say the square root of x squared plus y squared over k equals tangent inverse of y over x. Taking the arctangent and then multiplying by x, we could get y equals x tangent of square root of x squared plus y squared divided by k. However, we cannot get x or y alone. So this actually has a general name of the Archimedean Spiral. And it doesn't just model the nautilus shell, but it actually can model lots of other things in nature. So how can we describe this curve mathematically? Well, there's a descriptor. However, it's not a function, for one. You can tell that very easily. It repeats, our y values and our x values repeat several times in the xy plane. In the polar coordinate system, this is perfectly legitimate. I mean, this is a function in terms of theta. So, yeah, or in terms of theta and r. So this is as good as we can get in our Cartesian plane. The last thing we're going to look at is symmetry of polar curves and equations. So if we have a function r equals f of theta, okay, so this means that the point r theta is on our graph. Well, it is symmetric about the polar axis. That is what we'd normally call the x-axis. It's symmetric about the polar axis if r negative theta is also on the graph. similarly, the equation r equals f of theta is unchanged by replacing theta with negative theta. Now, an alternate way, something else you can check for this, is if negative r pi minus theta, if that is also on the graph. So if r theta is on the graph, then either r negative theta or negative r pi minus theta. Now, if you look at if you use what you know about trigonometry and angles, then that shouldn't surprise you from looking at a graph, and we see one in a second. Okay, second, it's symmetric about the pole, that is 0, 0, the origin. If every point r theta on the graph, if for every point r theta on the graph, r pi plus theta is also on the graph. Okay, alternate way to think of that is if negative r theta is also on the graph. And it's symmetric about the vertical line, theta equals pi over 2. I don't think that's considered a vertical line. No, that would go through the origin. The slope of 1, I believe. I think that actually might be a typo in the book. Okay, so if the point r pi minus theta is on the graph, and again, an alternate way to say that is what if negative r negative theta is on the graph? So we're going to find the symmetry of the rows defined by the equation r equals 3 sine 2 theta and create a graph. Alright, so let's go ahead and first check for symmetric about the polar axis. Let's evaluate r equals 3 sine 2 theta at negative theta. Alright, 3, don't need parentheses yet, sine of negative 2 theta, evaluating at negative theta. That is negative 3 sine 2 theta, which is not true. Okay, those two are opposites of each other. So that test did not work out. Not that. So let's go ahead and try the negative r pi minus theta, since those actually show us the same thing, but sometimes one is easier to see than the other. So if I say negative r equals 3 sine, and this is of 2 pi minus theta. Alright, well, we're going to have 2 pi minus 2 theta. Now, a trigonometric identity actually tells me this is going to be equal to negative 3 sine of 2 theta. And if you notice, this is the same equation we started with, r equals 3 sine 2 theta. If we divide by negative 1, then we have r equals 3 sine 2 theta, which means this is symmetric. Symmetric about the polar axis. Symmetric about the polar axis. All right, next, we want to evaluate at pi plus theta. Pi plus theta. So 3 sine 2 pi plus theta. That same identity from earlier tells me this is equal to 3 sine of 2 theta, which is the equation I started with. That's great. All right, so we have symmetry. It's symmetric about the pole, that is 0, 0. All right, now we want to test for symmetry about the vertical line, or the line theta equals pi over 2. Okay, good. It actually is a vertical line. That is not a typo. Just want to check that. Okay, so if it's symmetric about that vertical line, all right, so let's go ahead and plug in pi minus theta, which we are going to see is not going to work, just like it did not work in part A. Right, because we're actually going to have the same problem. We'll have a negative on one side but not the other. But if I take negative r equals negative theta, so this will be 3 sine of negative 2 theta. This is going to be negative 3 sine 2 theta equals negative r, which is the same as our original equation, so this is a check. This is symmetric. About theta equals pi over 2. So if we were going to graph this, nope, I don't have a graph there, or a grid. If I were going to graph this, based on this symmetry, we only need to graph one portion of this. So we have 0, 0, 0, 0. Pi over 6 is roughly 2.6. My graph is not going to be to scale. Pi over 4 we have at 3, a radius of 3. Next we get a 2.6 again at pi over 3. And then at pi over 2 we are back at 0. So we have a graph that looks like this. Based on it being symmetric about the pole, we know we're going to have another leaf on this end. Based on it being symmetric about the polar axis, we know we're going to have another leaf here. And then about pi over 2 means we are going to have another leaf over here. So that is the full picture of our graph based on, and this is a rows, but based on that one quadrant. All right, that brings us to the end of 7.3. I hope this makes sense. If not, you might watch this again, some notes and pieces, because this is a different way to think about our coordinate plane.